Hi, good afternoon. My name is Eric Kim, and as in the introduction, I work with Professor Nari Shambak, and in our lab, we concentrate on building reliable and low-power circuits or high-speed I/O that borrows ideas from communication. So basically, our lab uses communication-inspired ideas and applies them to circuits. So, as technology scales, in the nanoscale regime now, reliability has been a very strong issue. And one of the reasons is with each scaling technology, the supply voltage is lowered, resulting in a very low noise margin. So the charge that is needed to flip a logic bit has increased considerably, which results in a high rate of errors. And also with each process generation, the process variation increases about 20%. And in a current 32 nanometer technology, the channel dopant has around an average of 3.5 boron atoms, which you can say that some devices have 3 atoms and others have 4, which directly results in a 25% variation. So this process variation manifests itself as a widened delay curve here. So in older processes, if you have a nominal delay, most of the devices are concentrated around that delay with very few outliers. But in modern nano process technology, the delay curve is spread out, so you have a huge variation. So even though with the process scaling, the average delay decreases, the worst case delay may not necessarily decrease as much. So this results in, previously, if we were able to design for the worst case, in modern technology, that would be a very inefficient design. And also because of this long delay tail, designing for the nominal case would result in a very inefficient design. This is where robot system design techniques come in that will enable us to design at the nominal corner while still meeting the performance requirements. So first, before I explain soft NMR, I'll give you a brief introduction on NMR, which stands for N-modular redundancy. Here we replicate the blocks n times. We replicate the computation block n times, and then use a majority voter to combine the n outputs into one final vote. This can be viewed similar to repetition coding in communication. And due to the replication nature, the complexity is very high, so in practical scenarios, mostly triple NMR or TMR is most widely used. As the reason is DMR, as you can see, can only detect errors when the outputs are different, but there's no way to correct them. So soft NMR is a general technique, as is NMR, because here we have n replicas, same as NMR, but instead of a majority voter, we have a soft voter that makes use of estimation and detection techniques. So in communication language, once again, we can view the computation as a channel, because the computation is where we get errors into our system. It's equivalent to a communication channel. And then inside the soft voter, we have an estimator that can be viewed as an equalizer, and a detector that can be viewed as a slicer. So the soft voter uses estimation and detection techniques, and what this does is takes its inputs, which I'll be explaining, to find the most probable output. And one of the most important inputs are error statistics. So we have to characterize the errors that the circuit will exhibit, and then we can generate some sort of error statistics like this. This is a 16-bit ripple carry adder subject to voltage overscaling. So if there is a critical voltage that your circuit operates at, which the critical voltage is defined as the minimum voltage your circuit operates with no errors, reducing the voltage below that we would refer to as voltage overscaling, and that would make your circuit operate slower than the design speed, which results in timing errors, and we can characterize these errors to obtain a PDF like this form. And then we have a set of hypotheses. So this set of hypotheses will constitute the possible correct values that your voter assumes. So given these observations, your estimator would come up with a possible set of values that are correct. And then we would use the observations itself and estimate or detect over these inputs to find which of the hypotheses is the most probable one. So to further talk about detection, detection is a very simple process. You would just be computing this equation here, which is given each hypothesis, you would compute the probability of observing values. So if you have 3 replicas and you observe y1, y2, y3, and if you assume your hypotheses are also your observed values y1, y2, and y3, then under hypothesis 1, you would try to compute the probability of receiving y1, y2, and y3, given that y1 is correct. To do this, you would use the error statistics, so you would need to compute the errors that are in y1, y2, and y3, which would be subtracting your hypothesis from the observations. So you would compute the error in this as y1 minus y1, which would be 0, and then the error in this term, in this observation, would be y2 minus y1. The error in this observation would be y3 minus y1. And then assuming that all the errors are independent, you can just take the multiplication of those 3 probabilities. So you would compute this for your 3 hypotheses, and then you would choose the one with the maximum value as your final output. So combining these, we can come up with the soft voter algorithm. And right now, our algorithm is optimized for system reliability. So the optimal voter would be to compute the maximum of that probability. Here, the first term in the numerator is the detection term we saw earlier on, but you can see it's multiplied by another probability, which we refer as to the prior. So this would be the probability that that each value is actually observed. Okay, so this equation is a very complex equation to compute. If your output is 8 bits, then you would need to compute this equation for 2 to the 8 times, which is very impractical. So this equation is only used as a bound on performance of our soft voter. But more practically, we would limit our hypothesis to the observations as we did in the previous example. So if for TMR, you would have to compute this equation for only 3 times. And so this is the final soft voter equation that we use for our simulations. So this architecture is used in our soft voter. So if we notice that when all 3 inputs are the same, we would not even need to compute anything but just output the value directly. So we have a comparator that compares the values, and then when the comparator flags a difference, then we use the optimum rule block, which uses error statistics that are stored in the memory. And the power overhead of this soft voter is low, as the typical error rate is small for computation blocks. So the probability of this optimal block being activated is low, which results in a low power overhead. So before I show you the simulation results of soft NMR, I'll first explain the simple simulation procedure. So we first model our computation into structural Verilog based on basic building blocks such as adders and multipliers and AND gates and OR gates. And then we use HSpice to simulate each basic building block with different supply voltages and obtain a supply voltage versus delay curve. And then we take the delay numbers and plug it into actual Verilog codes to simulate the computation under various voltages. So this way we are able to simulate voltage overscaling, and from this we can obtain the error statistics that are shown on the right side. And also we use HSpice to get power numbers for each basic building blocks and estimate the power of our entire circuit. So under this, we simulated a 2D DCT block, and these are just error statistics of two different operating voltages, 1 volt and 0.8 volts. And here we see the supply voltage versus the component, the error probability of our computation block. Since the y-axis is in a logarithmic scale, we can see that error probability increases very rapidly with decreasing supply voltage. And this is the block diagram of our simulation. So a conventional DCT would have only one block, and we would go through the entire chain. And then we would also do soft DMR, because the soft voter is able to distinguish between two values as we're trying to find the most probable one. And then we have soft TMR that has 3 replications. So the simulation results show if this is the original image, and this is just the image through a DCT with no errors. You can see the conventional one with errors is completely distorted. You cannot tell what the original figure was, whereas in TMR you can barely see the outlines of the figure. However, soft DMR and soft TMR are shown to prove that they can considerably reduce the errors. So, yes. So if you plot the probability of error versus PSNR, you can see soft TMR constantly achieves around 10 times better performance than TMR, while soft DMR, even though it has one less replication, achieves up to 2 to 4 times improvement in PSNR. And this voltage can also be translated into power, as the lower supply voltage means power savings. If we draw the axis in terms of PSNR versus power, we can see that soft DMR achieves around 40% power savings due to the fact that one replication is reduced. And then soft TMR also reduces power, as the reliability can be traded off for reduced supply voltage. So this is a complexity comparison of the voters. For TMR, a word voter is around 432 transistors, which is only a 0.1% overhead in complexity and negligible power overhead. And soft DMR and soft TMR, you can see, is a very complex voter. So the complexity overhead is more than 10%. However, the power overhead is very small due to the fact that, as I mentioned, the soft voter is activated only when the inputs are different. And also, most of the complexity is due to memory to store the error statistics. However, the memory is very efficient power-wise, so the power overhead is not that big. So, in conclusion, soft NMR exploits error statistics to achieve around 10 times enhancement and around 40% power savings over conventional NMR. And this shows that exploiting error statistics and doing these stochastic computation can result in a very robust system design technique. And in the future, currently we are doing research on exploiting the spatial and also temporal correlation between errors, as we assume the errors to be independent. And also, we have many methods of expanding the hypothesis set. Right now, our hypothesis is based on only the observations we have. And also, we're going to do sensitivity studies on the error statistics versus performance. And we have a chip implementation of this planned for the future. So, thank you.
So, we have time for questions. Is there any questions?
Yeah.
So, I guess you said about the memory that you have to use a lot of memory to store the hypothesis, right?
The error statistics, yes.
Is there some way to model it in some way? I mean, it looks, in the way you had plotted it, looked like some kind of Gaussian or something fitted.
Actually, VOS errors are they're very spiky in nature, because most computation is done LSB first, so your most significant bit would be the last to complete its computation. So timing errors are circuit making errors because there isn't enough time to finish the computation. So when you have timing errors, they are mostly in the MSB. So it's not exactly a Gaussian distribution. And this is one of our research topics that we are looking for. So this sensitivity study is actually a study on the sensitivity of your error statistics to the performance of soft NMR. And one of the studies that will be done is what happens if we sort of approximate the error statistics, what the precision needs to be, what happens if we group some points together into one statistics, and so on. So that is an ongoing research we are doing right now. Yes?
See, the overhead doesn't count the triple redundancy, right?
Oh, the overhead is compared to...
Just the voting part.
Yes, just the voting.
So my question is, how much do you gain from the triple redundancy? I mean, if you use 3 times the power on one copy versus a triple redundancy, how does that compare?
Yeah, so the way this is set up is we have 3 replicas. So our baseline comparison is TMR actually. We are comparing all our simulation data to TMR. So
TMR is which?
This red one is TMR. So
yeah.
Conventional TMR would perform this much, but using our soft voter, we are able to push it up to this purple curve.
Yeah, but my question is, how does TMR maybe compare with no redundancy?
So there is complexity, and that's the price you would have to pay for increased reliability. But TMR is used in many systems today, so yes, so soft TMR is looking to replace those systems.
Any other question? So I have a question. So you present an optimization problem in your slide. So what is the nature of the problem? Is it complex, or which algorithm have you used to solve it?
So by optimization,
This one?
You're referring to this?
Mm-hmm.
So this is just using the maximum, it's the map rule in communication. So yes, it's just maximizing it's choosing the hypothesis or choosing the value that gives you the maximum probability. So if you plot it out on each point, your curve would have one maximum point. But
So you just compute all the values and
yeah,
see which one's largest?
it's not necessarily a continuous graph, so...
So is it combinatorial problem?
Yes.
So have you computed the complexity?
Yes, so this equation is very complex to compute. I mean, each computation isn't that complex, but you have to compute a significant amount of data to find the maximum. It's not like you find your way to the maximum point. You have to compute all the data points to find the maximum.
Okay. Okay, thanks for the speaker again.